All right, so if you've ever found yourself wrestling with the, well, let's just say, challenging dynamic equations of AC machines, you know exactly what a headache they can be. Today, we're going to look at a really powerful tool that just cuts right through all that complexity with some, remarkable elegance. We're talking about the space vector.
So here's the plan. We'll start with what I call the winding problem. Then we'll introduce the space vector as the solution. After that, we'll get into the nitty-gritty of defining the machine vectors and what they actually mean physically. And we'll wrap up by connecting all of this back to something you already know pretty well: phasors.
Okay, Section 1, the winding problem. So what is the real challenge with time-varying mutual inductance? Well, let's get right into it. The single biggest hurdle when you're trying to model an AC machine, especially dynamically, is the magnetic coupling between the stator and the rotor. See, this coupling isn't some nice, neat constant. Nope, it's changing every single instant that the rotor is spinning.
And if you look here at equation 219 from our text, it just perfectly illustrates the issue. You can see right there that the mutual inductance between the stator and rotor phases, it depends on the cosine of the rotor's angle. What does that mean for us? It means our equations of motion have coefficients that are changing all the time. And believe me, trying to solve that directly is a real nightmare.
All right, Section 2, introducing the space vector. So how do we get around this problem? How do we combine three phases into just one concept? Well, this is where a really brilliant mathematical abstraction comes into play: the space vector. The whole idea is, instead of fighting with three separate interacting phase quantities, we're going to combine them all into a single, unified thing.
So, yeah, that's the big question, right? How can we possibly represent these three separate, interacting magnetic fields as a single, unified entity? That's what we're aiming for. We need a way to capture the total effect of all three stator windings at any moment in time, but with just one single mathematical object.
Okay, so the key to this is to start by thinking about each phase winding, phase A, B, and C, as producing its own magnetic field, its own magnetomotive force, or MMF. And this figure right here, figure 2-6, shows us exactly how to visualize that. We can represent each of those fields as a vector, and the direction of that vector is just lined up with a winding's magnetic axis. These three little vectors, they are the building blocks for our big space vector.
Right, Section 3, defining the machine vectors. We've got our individual phase vectors, so how do we actually combine them into a single resultant vector? Let's get into the math and see how it's done.
This page right here, from the source material, this is where it all comes together. It lays out the mathematical foundation for us. It shows exactly how we define these resultant space vectors for all the key electrical quantities in the stator.
And here it is, equation 220. This is basically the magic formula. It tells us that this resultant MMF space vector, it's just the vector sum of the instantaneous MMFs from phase A, phase B, and phase C. You just add them up vectorially. And just like that, poof! We've gone from three complicated interacting things down to one single elegant vector. It's really that simple.
And you know what? This brilliant idea doesn't just stop with MMF. We can apply the exact same principle to define space vectors for stator current, for voltage, and for flux linkage. The logic is absolutely identical. You take the instantaneous values from the three phases, you combine them, and you get a single resultant vector for each one.
Okay, Section 4, the physical interpretation. Now, the math is, well, it's pretty slick, right? It's clean, but it's easy to get lost in the abstraction. So what does this space vector actually represent physically? Like, what's happening inside the machine?
Believe it or not, the physical meaning is surprisingly simple and just as elegant. Look at figure 2-7b here. It helps us see exactly what's going on. That stator current space vector, it physically represents the MMF you would get from a single hypothetical winding. Just imagine for a second that instead of three coils, you had just one, and that one coil produced the exact same magnetic field as all three phase windings working together. That's it. That's what our space vector represents.
So here's the crucial takeaway. This is the whole point. We can now analyze the entire machine as if the stator only has one winding, and the magnitude and orientation of that one winding, they're just described by our space vector. This just massively simplifies everything, how we visualize it, and, more importantly, how we calculate it.
And right here, this quote, this shows you the real payoff. This isn't just a neat academic trick.
The simplification extends directly to calculating electromagnetic torque. And if you're designing high-performance electric drives, this is an absolute game-changer. It means that the super complex torque calculations you need for real-time control suddenly become fast enough to actually run on a microprocessor. This is what makes modern vector control possible.
Okay, last section. Section 5, Connecting Vectors and Phasors. Let's take this powerful new tool and connect it back to something you're probably all very familiar with from your circuits classes, the phasor. It is absolutely vital to understand how they relate, but also how they're different.
And this page from the source material really breaks it down for us. It gets into the details of the relationship. So let's dig in and see how they compare and contrast.
So here's the absolute key difference, and you gotta get this straight. It's all about domain and application. A space vector lives in the time domain. It represents the instantaneous spatial MMF at a specific moment in time. That's why we use it for dynamic and transient analysis. A phasor, on the other hand, lives in the frequency domain. It only represents the magnitude and phase of a nice, clean sinusoidal signal in steady state. Totally different jobs.
But, and this is the really cool part, there's a crucial link. Look at these two figures. When the machine is running in a nice, balanced, sinusoidal steady state, the space vector and the phasor are directly related. In fact, at time t equals 0, as you can see here, they actually point in the same direction. Their magnitudes are just off by a constant. This provides a really powerful bridge between the world of steady state and the world of dynamics.
And why does this bridge matter so much? Well, because this relationship is incredibly useful. It means we can start our analysis in the easy world, right? We can use simple phasor calculations to figure out the initial conditions of the machine when it's just humming along in steady state. Then, when a load suddenly changes or something dynamic happens, we can seamlessly switch over to our more powerful space vector model to predict what's going to happen next. It's really the best of both worlds.
So, I'll leave you with this thought. We now have this incredibly powerful tool, this framework that takes a complex three-phase machine and lets us think about it as a single vector. So the big question is, how can we now use this tool to predict and, more importantly, control the machine's behavior under really dynamic conditions, like a sudden massive change in load? Answering that question, well, that's where we're headed next. And that's where the true power of space vectors really shines.
All right, anyone who's ever tried to wrangle the dynamic equations for a three-phase machine knows it can be a real beast, right? Well, today we're going to talk about a really powerful mathematical tool that cuts right through all that complexity. It's called the space vector. So let's just dive right in. Okay, so here's the plan. We'll start with the problem, the big challenge with three-phase machines. Then I'll introduce you to our hero, the space vector. We'll talk about what it actually is in the physical world, clear up that classic confusion between space vectors and phasors, and then, and this is the important part, we'll see why this whole concept is so crucial for pretty much all of modern motor control.
So let's get into it. What is the big deal? Why do we even need a new approach for this? Well, the problem in a nutshell is that in any AC machine, everything is, well, it's moving all the time. The magnetic fields aren't just changing in strength, they're physically spinning around as the rotor turns. And that means our key parameters, things like inductance, they're not constants anymore. They're moving targets.
And yeah, this equation right here, this is the problem in a nutshell. You see that law L, that mutual inductance, it's a direct function of theta m, the rotor's angle. So every time that rotor moves even a tiny bit, this value changes. Now imagine trying to keep track of that, not just for this one interaction, but for all the windings, all at once, in real time. It turns our math into an absolute nightmare, especially when we want to do any kind of dynamic control. There's just got to be a better way, right?
Well, there is. And that better way is the space vector. You can think of it as a really clever mathematical transformation. Its whole job, its entire reason for being, is to take that messy, multi-phase, position-dependent system and just simplify it, to make it clean and elegant. So let's just pause and think about this for a second. What if we didn't have to track three separate, messy, time-varying currents? What if we could boil down their total combined magnetic effect into one single, elegant entity? Well, that's it. That's exactly what a space vector is. It's one vector that at any single moment in time tells you two things: the total magnitude of a three-phase quantity, like current or flux, and, critically, its physical spatial orientation inside the machine's air gap. The two keywords to burn into your brain here are instantaneous and spatial. And this picture here shows it beautifully. You see the individual magnetic fields from each phase. You've got phase B, and phase C, and each one is pointing along the axis of its winding. The space vector, this Fs right here, is literally just their vector sum at that one specific snapshot in time. It captures the net result of all three phases in one single tidy vector.
Okay, I get it. Right now, this probably still feels a little bit like abstract math, so let's bring it down to earth. Let's talk about the physical interpretation. For a lot of people, this is the real aha moment, where it all just clicks. This slide, this is the whole game right here. Look at the left, that's the real machine. You've got your three separate windings. It's complicated. Now look at the right. That's a conceptual model. It's just one single hypothetical winding. And here is the absolute key. We can define the current flowing through that one winding, and we can define its physical orientation so that it produces the exact same magnetic field as the three real windings on the left. And don't just take my word for it. This isn't just some loose analogy. The source material spells it out. The stator current space vector can now be visualized by a current equal to its peak value flowing through a hypothetical sinusoidally distributed winding. So this gives us a totally rigorous way to swap out the complexity of three interacting phases for the beautiful simplicity of one equivalent winding. And that simplification, man, that is incredibly powerful. Okay, so right about now, I know what some of you are thinking. You're thinking, hold on, a rotating vector that represents AC quantities, isn't that just a phasor? And you know what? That is an excellent question. It's probably the single most common point of confusion, so let's just clear it up right now. The difference is absolutely fundamental. Let's break it down. A phasor, which you all know and love, represents a single quantity that's varying in time. It's a great tool for steady-state analysis, right? But a space vector is totally different. It represents the combined spatial distribution of three quantities at one single instant. Its length is the magnitude of the field right now, and its angle is its physical direction in the machine right now. So phasors are about time, space vectors are about space. Phasors are for steady state, space vectors are built from the ground up for dynamic analysis.
Now, to be fair, there is a connection. If you have the perfect, idealized scenario, balanced, sinusoidal, steady state, then yes, as this figure shows, there's a direct relationship between them. But that's the only time they're that simple. The space vector is so much more powerful, so much more general. It still works perfectly during transients, when things are unbalanced, even with non-sinusoidal waveforms. All the messy real-world stuff we actually have to deal with when we're designing high-performance drives.
Okay, so let's tie this all together. Why on earth did we go through all this trouble? What's the big payoff? Well, the payoff is absolutely huge. Because this concept, this is the mathematical key that unlocks the door to basically all of modern AC motor control. You see, this whole transformation from three phases down to one vector, it's not just some neat trick to make the homework easier. It has profound practical consequences. For starters, those nightmarish dynamic equations, they suddenly become simple enough that a little microprocessor can solve them in real time. That's a game changer. Second, we can now calculate the machine's torque directly from this one vector. No more messing around with individual phases. It's faster, it's more direct. And here's the big one. This simplification is the foundation for our most advanced control strategies. We're talking about field-oriented control, or FOC. That's the gold standard. It's the brains inside pretty much every high-performance drive you can think of, from an electric vehicle to a high-precision factory robot. So let me leave you with this thought. We've done something pretty amazing. We've taken this complicated, messy, physically spinning three-phase system, and we've managed to describe its entire magnetic state with one single, beautiful, manageable vector. So the next logical question, and really this is the question that drives the entire field of modern control, is this. Now that we have it, how do we control it? How can we manipulate that vector's magnitude and its direction millisecond by millisecond to get any speed or torque we desire? The answer to that question, well, that's where things get really, really interesting. All right, everyone. So far, we've spent a lot of time looking at machines in steady state, which is great, but it's not the whole story. Now we're going to dive into the really interesting stuff, the dynamic behavior of induction machines. And to do that, we're going to need a powerful new tool in our toolbox, space vector theory. So here's our roadmap for this explainer. We're going to start with the physical basis, the nuts and bolts of what's happening inside the machine. From there, we'll build up to the mathematical model and, most importantly, see how it's actually used in practical applications. Let's dive right in. You might be asking, why do we need to go beyond the simple phasors we already know and love? Well, if you want to truly understand and control a motor during startup, or when the load suddenly changes, or during a fault, you need a method that works under dynamic, changing conditions. Phasors just aren't built for that. And this image really gets to the heart of the problem we're trying to solve. We've got 3 distinct phase currents, each creating its own magnemotive force, or MMF. And all 3 of these are interacting within the machine's air gap. It's a complex dance, and trying to track each one separately is, well, it's a real mess. So let's move on and see how we can build this up from first principles. The entire theory of space vectors, believe it or not, starts with a fundamental physical principle that you already know: mutual inductance. Now, as the rotor turns, you can see that angle, theta m, is constantly changing. This causes the mutual inductance between the stator and rotor windings to vary sinusoidally. This is it. This is the physical interaction we absolutely need to model to understand what's going on. So here's the crucial insight. We can represent the magnetic field from each individual phase winding as a vector. Now, think about this. The direction of that vector is fixed in space by the physical axis of the winding. But its magnitude, its length, pulses in time with the instantaneous current. Okay, so we've got 3 separate vectors, all pulsating away. But instead of tracking all 3 of them, what if we could combine their effects into a single, unified vector? That's the leap we're about to make. And here's how we do it. Assuming we're not saturating the iron in the machine, we can simply use the principle of superposition. We just perform a vector sum of the 3 individual phase MMFs. What we get is a single resultant space vector that perfectly represents the total air gap MMF at any given instant in time. Now, what's really interesting here is how we translate this into mathematics. Look closely at those equations. You see those complex operators? The e to the j something? Those aren't about time. These are spatial operators. They are what place each phase at its correct 120 and 240 degree physical position inside the stator. It's a key distinction. All this complex math, it leads to a brilliantly simple physical interpretation. And this, right here, this is the real aha moment. This is the power of this entire approach. And this illustrates that concept perfectly. On the left, you've got the 3 pulsating phase currents, but their combined effect, on the right, is perfectly equivalent to a single resultant vector that represents the entire magnetic state of the machine. It's so much simpler. This allows us to imagine a single hypothetical winding. Just one. This idea simplifies incredibly complex tasks, like calculating the machine's electromagnetic torque, because now we only have to worry about 1 winding instead of 3. It's a game changer for analysis. Now, I know many of you are very familiar with phasors from your circuit analysis courses, so it is absolutely critical to understand how space vectors are different. They're related, for sure, but they represent fundamentally different things. So here's the key takeaway. Phasors are for steady-state analysis. They describe the magnitude and phase of a sine wave, and that's it. Space vectors, on the other hand, capture the instantaneous physical state of the machine. They're like a live snapshot, which makes them essential for dynamic control. But under certain conditions, they do connect. If you have a perfectly balanced, steady-state condition, at the specific instant in time when t equals 0, the space vector and the corresponding phase A phasor will actually align perfectly. They'll point in the exact same direction. And that alignment naturally raises a crucial question about their magnitudes. Okay, if they're pointing in the same direction, does that mean they have the same length? Is the amplitude of the phasor equal to the amplitude of the space vector? The answer is a definitive no, and this is a point you absolutely must remember. Because of the way the vector projections of the 3 phases add up, the space vector's amplitude is 1.5, or 3/2, times the phasor's amplitude. This is a critical conversion factor you'll use all the time. Okay, let's wrap this up by looking at the practical workflow and summarizing what we've learned. How do we actually use this in practice? This is how it's done. You often start a simulation from a known steady state. So step 1,
You initialize your conditions using simple phasor analysis. Step 2. You convert those phasor values to space vectors using that critical 3/2 scaling factor. And finally, step 3, you simulate the machine's dynamic response using the full space vector equations.
So to recap, space vectors give us a way to represent the physical MMF in the machine. They let us simplify the complex three-phase system down to a single hypothetical winding model, and they scale by a factor of 3/2 relative to phasors, which is what enables us to bridge the gap and perform dynamic simulations.
And this brings us to our final thought for today. We've done all of this in a stationary reference frame, one that's fixed to the stator. But for high-performance control, it's often way, way better to have a reference frame that actually rotates with the rotor field. And that idea is the entire topic of our next lecture on DQ transformations. Thanks, everyone.
All right, welcome everyone. Today, we're going to jump right into a really core concept for machine analysis, and that's space vector theory. Think of it as a special lens that lets us see exactly what's happening inside the machine, especially when things get dynamic.
So here's how we're going to break it down. First, we'll look at the actual physics inside the motor. Then we'll define what a space vector even is. After that, we'll see this really cool trick, the hypothetical winding model. And finally, we'll tie it all back to something you're probably already familiar with, phasors.
Okay, so before we dive into the math and the definitions, let's talk about why we even need this tool. You know, what's the problem we're actually trying to solve here? It all starts with what's physically happening inside the machine. So, at the heart of any electric machine, you've got this, well, it's like a magnetic dance between the stator and the rotor. And the problem is, as you can see here, the coupling between them, what we call mutual inductance, it's not a constant number. Nope, it changes with the actual physical angle of the rotor. So as that thing spins, the math gets messy, right? The equations become dependent on position, and that's just a massive headache to work with. There's got to be a better way.
And that's where the space vector comes in. The big question is this: how can we possibly take three different, constantly changing phase currents and boil their combined magnetic effect down to just one thing at any single moment in time?
Well, the way we start is pretty smart. We look at each phase one by one. So you've got phase A, phase B, and phase C. Each one at any given instant is creating a magnetic field, what we call the MMF. And we can think of that MMF as a little vector. The direction of that vector? It's locked in place by the physical winding. The size of the vector? Well, that just depends on how much current is flowing through it right at that second.
Okay, now here's the cool part. We can just add them up, right? Assuming we're not saturating the iron, we can use superposition. We literally just take the vector from phase A, add the vector from phase B, and add the vector from phase C. And what do we get? We get one single resulting vector. And that one vector, that tells us everything about the total magnetic field from the stator at that exact instant.
Now, I know this equation looks a little scary with all the e to the j stuff, but don't let it fool you. This isn't about time, it's about space. The key takeaway here is that these complex operators are not phasors spinning around. Think of them more like address labels. They just tell you where each winding is physically located. Phase A, that's at 0 degrees. Phase B, that's at 120 degrees. And phase C is at 240. That's it. All they do is point each current in the right physical direction.
So, where does all this lead? To a really powerful simplification. I mean, what if we could take this whole messy system of 3 windings and just replace it with one? This is really the aha moment of space vector theory.
And this picture says it all. Look at the left. That's the reality, right? 3 different windings, 3 different currents, all interacting. It's complicated. Now look at the right. That's the beauty of the space vector. We can represent that entire magnetic mess with just one single imaginary winding. It's the same exact effect, but way, way simpler.
And here's the bottom line. This hypothetical winding, it's not physically there, of course, but it acts exactly like the real three-phase system. It makes the same magnetic field, it has a current related to the peak, and it points in a specific direction. So why do we care? Because now, when we want to calculate something like torque, we only have to deal with one winding. For anyone designing a drive controller, this is an absolute game changer. Your algorithm doesn't have to juggle 3 variables anymore. It just has to control one vector. That's what makes modern, high-performance motor control even possible.
Okay, this is great.
we've got this awesome new tool. But you're probably wondering, how does this connect back to phasors, the stuff we learned in circuits class? And more importantly, how do we actually use this for analyzing the dynamics of a real drive system?
This table really lays it out. Think of it this way. Phasors are fantastic for steady state. When everything is a nice, constant sine wave, phasors are your best friend. But drives live in the real world. They speed up, they slow down, the load changes. For that kind of dynamic action, you need space vectors. They give you a snapshot of what's happening right now at any instant.
But here's the thing. They aren't totally separate worlds. There's a bridge between them. Imagine you're in a perfect steady state situation. If you hit pause at the exact moment t equals 0, something cool happens. The space vector for the current will be pointing in the exact same direction as the phasor for the phase A current. They line up perfectly. That's our connection point.
Okay, but here's the catch, and you absolutely cannot forget this. Their directions match, but their magnitudes do not. Because of how we add those three vectors together, the space vector's magnitude will always be 1.5 times bigger than the phasor's magnitude. That 3/2 factor is super important. You have to remember it when you're converting between the two.
So, what this all means is that we have a really practical way to do our analysis. Here's the workflow. Step 1, you can start with the easy stuff. Use phasors to figure out your initial steady-state conditions. Step 2, you take those phasor values and you multiply by that magic 3/2 number to convert them into space vectors. And then, step 3, you're ready to go. You can now use the much more powerful space vector equations to simulate what happens when things get dynamic.
All right, let's just do a quick recap. First, space vectors come from the real physical magnetic field in the machine. Second, they let us pretend a three-phase system is just a single winding, which makes life so much easier. Third, they connect back to phasors through their direction and that critical 3/2 scaling factor. And finally, the whole point is to give us the tools to handle the dynamic, messy, real-world behavior of electric drives.
So, that leaves us with one last big idea to chew on. We did it! We managed to describe the entire stator's magnetic field with just one single vector. Awesome! But in an AC machine, that vector is always spinning. So here's the question. Why are we standing still watching it spin? What if we could just jump on and spin along with it? What if our coordinate system rotated too? Well, that's the whole idea behind DQ transformations, and that is exactly where we're headed next time.